Welcome back to ECE 501B. Homework number 2 is due Friday, like homework 1 was due last Friday. And today what I want to do is continue moving through Chapter 2 material, and we will quickly review the early part of Chapter 2 that we've effectively already covered, which is Chapter 2 is dealing with finite dimensional vector spaces. And we've talked about span, what that means for vectors to span some part of a vector space. We've talked about a collection of vectors, their span actually spanning all of the vector space, and we refer to that as W spans V if W represents this entire spanning list. We've also talked about what it means for vectors to be linearly independent. And then we just started discussing linear dependence via the first half of the linear dependence lemma, and we'll pick up at that point with new material. We'll start talking about bases, not first, second, and third or home base, but the basis of a vector space and what that means, and that's the plural. I don't know if you'll be able to hear that in my enunciation, but there are bases and there are basis vectors, meaning we can have many different basis vectors, and a basis is a linear independent set of vectors that spans all the vector space. And that will hopefully make more sense as we get to that point. We will then be able to introduce dimension. What does it mean to say, oh, this vector space has dimension little n? And that dimension of the vector space, dim of v, is really just the length, or how many vectors it takes to form a basis of that vector space. Those are the concepts we want to talk about today. As a review of the first part of Chapter 2, which Chapter 2 is talking about the finite dimensional vector spaces, let's talk about span. And suppose that the vector space that we're interested in is 3 space. So you can think of it as this room. We have, let's say, the horizontal in, let's say, 2 directions, x and y, and then we have the vertical y. The span of 1, 0, 0, and 1, minus 1, 0, and you can think of that as the x direction, and then going x and minus y. Those 2 vectors really are equivalent to just the xy plane in all of R3, because you can get anywhere you want in the xy plane by a linear combination of the x direction and this vector that is x and minus y. Those are not on top of each other as vectors, and they are now able to span all of the xy plane. There is no coordinate in, let's say, the z direction in those 3-dimensional vectors. And for that reason, then you can say the span of those 2 vectors is equivalent to covering or spanning all of the xy plane and nothing in, let's say, the vertical direction in the z. When we have a set of spanning vectors that span all of the vector space V, suppose we call that set W just to collapse it down, and maybe W is consisting of 4 vectors, W1, W2, W3, W4, then we say W as a set spans the vector space V. And W1, W2, well, we'll get there, I guess, in a minute, but we could have overlap in the W1, W2. This is just a spanning list, and it actually spans V. We're not saying anything about the linear independence or dependence of those vectors, W1, W2, W3, or W4. We're not saying anything about that here. We're just saying that if you had those four vectors, they would span the vector space V. And V we haven't defined, but if you needed something to sort of think about or hang your hat on, V might be R2. Maybe that's the XY plane. And you could now have W1 being the X direction, W2 being the Y direction, W3 being XY, W4 being minus X. Those span all of R2. And so the span of those four vectors would equal V, or W spans V. To get us where we want to go in today's talk, we need to sort of take those two ideas together. We need something that spans the vector space, but we would also like to have sort of a minimal set of vectors, and we can obtain that by talking about linear independence of the vectors. If we have n vectors, v1, v2 through v sub n, and if those are linearly independent vectors, then the only way for us to take a1 through an scalars in the field such that when we linearly combine all of those n vectors, and though their sum equals 0, the only way for that to happen, if those vectors are linearly independent, is for those scalars to all be identically 0. That's what it means to be linearly independent. You can contrast that with this concept of linear dependence. If we have linear dependence among vectors, then we can actually write one of the vectors in that set as a linear combination of the others. If you are given a set of vectors and they are linearly dependent, then you can find at least one of those vectors that can be written as a linear combination of the others. That's what it means to be linearly dependent. And here Wm can be written as, let's say, a linear combination of W1, W2 up to W sub m minus 1, where we have, if we needed to, maybe relabeled those vectors so that W sub m, which is the dependent vector, is the last one in that list of vectors. Those are then this concept of linear independence and linear dependence, and that leads us then into this linear dependence lemma that we sort of finished up with last time, and it's a little bit wordy, but it says it is possible to find an element of the list that can be written as a linear combination of the remaining elements. That's really what we just said above in the linear dependence. That is, one element in the list is in the span of the other elements in the list. Now let's put that into a more concrete example just so that we have something to think about. Suppose that you're given a vector W1, and let's play in R3. Let's say it's 1, minus 2, 1. And suppose W2 is now minus 2, 1, minus 1. And W sub 3 is minus 4, 2, minus 1. If we wanted to, we could say we have this list of vectors we will collect as W into this collection W1, W2, W3, where these are the vectors that we've just identified. Are those vectors linearly independent or linearly dependent? And it may not be obvious from inspection, but maybe it is. If you look at that, you can actually rewrite W sub 3 as a linear combination of the first two. W3 is minus 4, 2 minus 1, and that's equal to something times 1 minus 2, 1, plus something times minus 2, 1, minus 1. There are several ways to get the first component, but maybe not to match the second two. But if you now take 2 of the first, then you would need 3 of the second to get the first component. And in fact, if you take 2 of the second component or coordinate, which gives you minus 4, am I doing this right? Why is that not looking like it's correct? I can change it to be correct, can't I? Why don't I do that? So what would we do? What would we get if we did that? So if we have 2 omega 1 plus 3 omega 2, what do we now have? The first coordinate looks okay. Is that true? We have 2 minus 6, or minus 4. The third coordinate is, taking the last one, minus 3 plus 2. That's minus 1, so that's okay. So now let's change that. We can make them dependent, can't we? So now I have minus 4 plus 3. Is that true? So that one needs to be a minus 1, which says that I needed to have this guy equal to a minus 1 to make it nice, to make my example work out. Is that true? Is the algebra now correct? Meaning now W sub 3, maybe that's why it wasn't so intuitive the first time for you to see that combination. Now we can say that W sub 3 as a vector is actually contained in the span of W1 and W2. That's the first part of this linear dependence lemma, that you can write at least one of the vectors in your list, if this list is a linear dependent list, as a linear combination of the other vectors in the list. A second piece of that linear dependence list, or another way of sort of looking at the linear dependence lemma, is removing a linearly dependent element from the list obviously produces a new list. But if the element that we removed was linearly dependent, what have we done to the span? So if I have a collection of vectors and there's linear dependence, and I find one of the elements in that span or in that list that's linearly dependent on the others, and I remove it, what has happened to the span of the original set of vectors? It's unchanged, isn't it? We haven't done anything. So that's what I'm trying to say here. Removing a linearly dependent element from the list produces a new list with the same span as the original list. And we can prove that. Let's start with a linearly dependent list, or given a linearly dependent list of vectors. Let's call that list W, and maybe the elements in that list are v1, v2 up to vn. Those are our n vectors in this linearly dependent list. And a vector that is in the span of this list. And let's let that vector be u. So we're saying u is in the span of W. That's a given. So now we're assuming we have a linearly dependent list, W, and now we find a vector u, some generic vector u that's in that span of W. What does that actually mean? If you had to write u, the letter u, which is representing an element that's in the span of W, how could you express that? Or how have we done that before? What does it mean for u to be in the span of W? How would you write that? Correct. So we simply have to express it as a linear combination of the vectors, and a linear combination just means we take scalars from our field and scale the vectors and add them up. And we may have an interesting time trying to find those scalars, but if u is an arbitrary vector, then we can say u is alpha 1 v1 plus alpha 2 v2, etc., up to alpha sub n v sub n, for some set of scalars, alpha 1, alpha 2, up to alpha sub n. We now have a u that's linear, or that's in the span of W, and W is made up of these v's. But we said that that list was linearly dependent. So something in that list of n vectors, v1, v2, is linearly dependent. Suppose that we've labeled that such that v sub n is the linearly dependent vector. So now let's say, but we can express v sub n in terms of the other vectors. And here I'm suggesting by the appropriate labeling of all of these other, or of the vectors, v sub I of that in that list. That means that we can say v sub n is minus a1 over a sub n v1 minus a sub 2 over a sub n v sub 2, etc., where we have created this combination knowing that we had a dependence among those vectors, meaning we could have an a1 v1 plus an a2 v2 plus an a sub n v sub n equaling 0, where not all of those a sub n's are equal to 0 if it's a linearly dependent set. if v1 through vn was linearly independent, the only way that that equation could be valid is if those scalars were all identically zero. And we've labeled this, since v sub n is the dependent one, we know that a sub n is non-zero, so we can divide by that. Now, if we know that v sub n can be expanded in terms of the first n minus 1 vectors, then in our expression for u, if we replace v sub n with what we've just done, now we've expressed u in terms of how many of the vectors? N minus 1. By this parameterization of v sub n, we can now say, so u is some beta 1 v1 plus beta 2 v2 plus beta sub n minus 1 v sub n minus 1. Where that's a linear combination of n minus 1 vectors. But what this whole thing is based on was u being an arbitrary choice of a vector in the span of our original set. Thus, u is now in the span of v1, v2, up to v sub n minus 1, and u was a completely arbitrary element of the original span v1, v2, up to v sub n, which now says that the span of v1, v2, v sub n minus 1 is the same as our original n vector span. Which is what we were trying to show. We were trying to show that if we remove a linearly dependent element from the original list that we have, then we are not changing the span of our original set. And we've now demonstrated that or proved that. Which is nice, which really means we can throw away things in this big spanning list of vectors if we need to, if we want to get it to be smaller in number. And we're not changing the span. If we throw away elements that are linearly dependent. There's a couple of results that come out of that linear dependence lemma. Two important results. From the linear dependence lemma. One is theorem 2.6, which says the following. In a finite dimensional vector space, we can make the following relationship between sets of vectors. The length of of every spanning list, whoops, let me qualify that, spanning list of vectors, so that's how many vectors are in this spanning list, and a spanning list is spanning the whole space, is greater than or equal to the length of every linearly independent list of vectors. So if we have a finite dimensional vector space and somebody gives us a bunch of spanning lists, which by definition those spanning lists span all of this vector space, and you may have set A, somebody else has set B, somebody else has set C, we can basically start throwing things away or out of those if there's some linear dependence, but the most we can throw away is until we get down to the set that's linearly independent, is sort of what that's saying, the number of elements in that list. The second idea or result is proposition 2.7, and this says that every subspace of a finite dimensional vector space is maybe the obvious, it's finite dimensional. And those two results make sense intuitively. So if you're starting with a finite dimensional vector space, it's not going to get any bigger on you. And if you take a subspace from that vector space, it's going to be finite dimensional. It's not going to somehow magically increase in dimension, a subspace of the original vector space. That now allows us to be talking about concepts that allow us to sort of describe or cover a vector space, and those are these basis vectors. So let's now talk about bases, which is getting us up a couple of pages beyond the linear dependence lemma. Here's what we mean by a basis. A basis of a vector space V is a linearly independent list of vectors that spans V. So if somebody says they have a basis for your vector space, then you know that that set of vectors is linearly independent and you can get anywhere you want in your vector space. It spans, that set spans the entire vector space. Some consequences of having a basis. One is that we now can sort of say that we have the ability to have a coordinate system. And that coordinate system could be described or defined by a set of basis vectors. Let's look at another proposition related to that. Proposition 2.8. Any element that lives in your vector space, or any element of the vector space V, is expressible as a unique linear combination of basis vectors. Another consequence of this basis is that the length of the list of basis vectors is equal to the length of the shortest spanning list. And you can see that from what we talked about before when we had this inequality sign. Meaning, if I gave you two sets, let's say I gave you a number length that was the length of a linearly independent list, and I compared that with the length of a spanning list, and now I wanted some inequality sign right there, which way would that go? I want the length of a linearly independent list, and how does that compare to the length of a spanning list? It's less than or equal, isn't it? The linearly independent list is now going to be less than or equal to the length of the spanning list. And that's since the basis, or since the basis is both linearly independent well, maybe I didn't want that. Let me say, since basis is both linearly independent and spanning, equality must be true. The other thing that maybe is nice or not nice, depending on your mood or how we're feeling, is that generally, what can we say about a basis? Is it unique or not? No. So there's generally no unique basis, which really says that there are many shortest spanning lists. Let's look at some examples. Just it's that time of the day. Sort of take a break from all this wording and let's think in some visual terms. And the visual terms will be all on paper. So I'm not going to have any show and tell other than what's going to be printed here or written down on my tablet. The first example, let's say that our vector space is something easy to think about. It's your desktop, R2, 2 dimensions. What's a nice basis for that? Well, we could have 0, 1 and 1, 0. And don't ask me why I wrote them in that order. That's the y direction and the x direction. Maybe I should have said x and y and just reversed those. But that is a basis. And this is actually a standard basis. And in this case, we have all of R2 is V. One vector, the first one is right there at, let's say, 0, 1. The other vector is over here at 1, 0. And we can get wherever we want. If somebody now said, take me to this point in R2 that's at 1, 1. Question? So yes, so we could, the question was, why did you list it as y comma x in terms of a two-dimensional? X comma y is also a standard basis. Really, yes, I would basically say they're the same, but if you're really concerned about the ordering of the vectors, they could be different. But they both form a basis. So this is now x comma y, let's say, is the one that I would more prefer to say is the standard basis. Question? So now the question was, do they have to be ones? Typically, your standard basis is normalized. We haven't gotten that far yet. We haven't talked about length or distance, but having a length of 1 is nice. So yes, it's nice to have a standard basis that's normalized in length. We won't get there until quite a bit further into the class. So what we've started with in chapter 1 is sort of talking about where we're playing in vector spaces. Those are very general concepts. Now we're trying to put some dimension on that, some concept of how many vectors do we need to sort of span this vector space. That's chapter 2, and we've restricted our attention to finite dimensional vector spaces. That allows us now to start building up or throwing things away in order to span this finite dimensional vector space. Here we are saying what's a nice way, a standard way to span R2. That's to sort of go in a unit direction in one direction, go a unit distance in a second direction, and if you had a third dimension, you would go a unit distance in that third direction. Now, how would we describe that blue dot in terms of this basis? And maybe what I wish I hadn't done it this way, but I'll keep going with that. So now I want to know if I wanted to label this as maybe A1 times, and now I'm going to convert them from rows to columns, 0, 1 plus A sub 2, 1, 0. How would I pick A1 and A2, or what would A1 and A2 be equal to in order to get me to that blue dot? And A1 and A2 could be the coordinates of that dot in this standard basis. Meaning if I now say, so those are both going to be 1s, aren't they? Because I'm going 1 in the vertical direction and 1 in the horizontal direction to get to that blue dot. So in this basis, I could say that the coordinates of that dot are A1 comma A2, with A1 being 1 and A2 being 1. So this is now going to be 1, 1 with 1, 0, 1 plus 1, 1, 0, or A1 is 1, A2 is 1, and it's kind of hard to tell which is which because, but A1 is associated with V1, where this is now let's say V1, and this is V sub 2. Suppose I gave you the following two vectors, 1, 1, and -1, -3. And I like to just if it's not clear initially, I like to just make a sketch and convince myself that, okay, this does look like, or it doesn't look like it's a basis for R2. So again, we're dealing with a vector space V that's all of R2. Is this a basis for that vector space? The first vector is 1, 1, so that's now this point, or that vector. The other one is -1, -3, and that's now this one. And maybe I want to view those as vectors, so here's -3, there's 1, -1, and there's 1. And since those are not lying on top of each other or going in the same direction, those do allow me to span all of R2, and they are linearly independent, and that's the definition of a basis. This set then, 1, 1 and -1, -3, is a basis. How is this basis different from the other base? Uh-oh, I don't like what's happening. This is not a good sign. So I'm going to keep talking and hope that this poor thing starts to respond. How is this basis set different from the previous basis set? Can you decide or say anything about one versus the other, or how are they maybe different? So now somebody's using a term that we haven't yet made it to, and we're not going to make it there for a while. Somebody said something about a dot product, and we're not really, it's not really allowed yet, but what are you meaning by a dot product? They are orthogonal. The first set was orthogonal, wasn't it? Technology. And I'm going to have a broken back by the end of this semester leaning over this contraption that I have to now do. They said they were going to fix this after the first lecture, and it's been a few lectures, hasn't it? I'm going to be orthogonal by the end of this lecture, aren't I? My legs and my trunk will be at right angles. Whereas the second set, so these were orthogonal vectors, the first set. This set is not, is it? This one is non-orthogonal. But that's okay. It's still a basis. But now, how would we write, what point do I want to now write? Suppose that I now want to express the point 1, 1 in terms of these basis vectors. So now I want some scalar multiple of the first vector, which is 1, 1, plus some scalar multiple of the second vector. And I think it's pretty easy to do that decomposition. Here, in order to make that happen, we just need b sub 1 to be 1 and b sub 2 to be 0. Or now if somebody said, oh, the coordinates that describe that same point are now 1, 0, whereas before it was 1, 1. Meaning the coordinates that somebody gives you to describe a location in your vector space depends on the basis vectors that you're using. Yes? So now the question was, can we have more than one solution for B1 and B2? And you're testing me, aren't you? Do you remember what was stated somewhere earlier on, and I think in this lecture? Do you remember? I thought it had just, there was a unique somewhere in one of these. So if you have a basis, a set of basis vectors, then you have a unique representation of some vector in that vector space in terms of that set of basis vectors. I don't think that's the way it was completely stated before, but now it's reworded. So yes, that's a good question, but now that's the only linear combination of B1 and B2 that will get you to that point if you have a basis, a set of basis vectors. Now, you can see that this representation in that basis, although it's getting you to the same point, is not the same as the representation of that point in terms of this basis set. Now we have A1 and A2 equaling 1, 1. Now somebody could say, well, my point's at 1, 1. And somebody goes, well, my point's at 1, 0. And you have to remember that you're both talking about the same point, just you've represented that point in terms of different basis vectors. What are some other examples that we could talk about? Suppose that I gave you the following set. Is that a basis of R2? Did I hear a not in there? That is not, is it? And why is it not? So if we sketch the picture of that, here's R2. That gets us there. And if we wanted to go here again, could we get there using this vector? No, we can't, can we? We can only go vertical. So this doesn't span that set, doesn't span R2. And we can't get to 1, 1 using a unit vector in the vertical direction. Again, we're dealing with R2 as our vector space, and now I give you 0, 1, 1, 0, and 1, 1. Is that a basis? Why not? It's not linearly independent, is it? There's some dependencies among those vectors. So this set is not linearly independent. If we sketched those, we would have that vector, we would have that vector, and we would also have that vector. Which another way of saying that is points in R2, and this is getting back to the earlier question before, now we don't have a unique way of expressing a linear combination of those vectors for any point in the vector space R2. Here, points in R2 don't have unique representations as linear combinations of those three vectors, 0, 1, 1, 0, and 1, 1. So now we have this concept of spanning list and linear independence. Their sort of combination. If we have a linearly independent set that spans the vector space, that can be used as a basis. Now let's talk about maybe what this particular example illustrates, which is theorem 10 in chapter 2. Every spanning list, so those three vectors right there, do those form a spanning list in R2? Yes, they do span all of R2. So every spanning list in a vector space can be reduced to a basis of the vector space. That's nice. So somebody gives you a spanning list, you go, oh, good. But now all you have to do is throw out what you don't need. And we'll develop techniques for doing that. But now let's just talk about this sort of in general, or prove this in general. Proof. Suppose we're given a list B, and let's say that's made up of these n vectors. And we're assuming that those vectors span all of V, so that those vectors span V. But now we're going to assume that that spanning list is not a basis. What's wrong with that list? It's a spanning list. It spans V, but it's not a basis. What must be true then? These are now linearly dependent, aren't they? These vectors. So from the definition, of basis vectors B must be a linearly dependent set. Now, from before, we talked about throwing out linearly dependent vectors, didn't we? And what did we do to the span? How did the span change or not change? It didn't change, did it? If we have a vector that's linearly dependent in our spanning list and we throw it out, we haven't changed the span of that reduced set. So from before, a linearly dependent list a linearly dependent list must contain an element that is expressible as a linear combination of the other elements. The linear dependence lemma shows that we can delete this linearly dependent element, delete this element without reducing the span of the list. So now if we remove that linearly dependent element from the list, we haven't changed the span of the list. If this new list is now linearly independent, what have we created by throwing away one of the vectors? A basis, haven't we? So if this new list that we've generated by throwing out a linearly dependent vector, if this new list is linearly independent, we have created a basis. And we are done. What if our list is linearly dependent after throwing away one? We can throw another one away, can't we? We can find another one that's linearly dependent and get rid of it. So now if the resulting list is still linearly dependent, we simply repeat the process. And we can go back to that set of three vectors that we had before. If we take the list say 0, 1, 1, 0, and 1, 1. That list spans all of R2. We're okay, that's a spanning list. But you told me it is not a basis because the vectors are not linearly independent. But it is not a basis. Can you think of a nice way to make it a basis? Throw out any one of them, but what would be a nice one to throw out? The last one, right? Just kick it off, the last one. That's the easy one to get rid of. If we select 1, 1, and remove it, then the new list, which consists of 0, 1, and 1, 0, that new list does form a basis. Now, with some theorems, they have corollaries. Corollary 211. Every finite dimensional vector space has a basis. That's nice. So now if you give somebody a finite dimensional vector space, they can find a basis for it. Which means what? What's the definition of a basis? Yes, a linearly independent list that spans the entire vector space. And that's doable, or that this corollary says every finite dimensional vector space has a basis. So what's a way of showing that or proving that? Proof. By definition, every finite dimensional vector space has a spanning list. That's really coming to us by the definition of finite dimensional. Well, if we have that much from our previous corollary, or from our previous, wherever it was, theorem, we can reduce that spanning list as much as we want until we've gotten just a linearly independent set. So we're basically done if we've found a spanning list. We just proved a basis can be generated from any spanning list. If we're counting, we're up to 12. So theorem 12 in chapter 2. Every linearly independent list of vectors in a finite dimensional vector space can actually be increased or extended to a basis. Because I could give you a linearly independent list that's maybe not a spanning list. This theorem says if I do give you a linearly independent set of vectors, you can actually grow it or extend it until it becomes a basis, if it's not a basis to begin with. And that's a nice thing. So we know how to remove from a spanning list to get a basis. We now have a theorem that says we can add to some linearly independent vectors to create a set that's a spanning list. Let's see if we can sort of show that or prove that. Given a linearly independent list let's say B, of vectors in a vector space V, that are not a basis of V. So that's our first given. Let's say that that's now V1, V2, up to, let's say, V sub n. If that set of vectors, and it's linearly independent, but it's not forming a basis, what do we know about B and its ability to span the vector space? It doesn't, does it? So B must not span the vector space, V, if it's not a basis, but yet it's linearly independent. So now, if that's the case, let's select an element, let's say U, that's in the vector space V, such that U is not contained in the span of B. So now think in very basic terms. Let's say that V is a three-dimensional space, R3. And now I've given you basically vectors that are linearly independent. Let's say I've given you the x direction, the y direction, but I haven't given you z. So now select a U that maybe has a non-zero z coordinate. It could have x's and y's in it, but we need it to have, whoops, what did I, so I don't want it to be in the span of B. Sorry, I didn't finish my sentence. So now U, we want it to be in the vector space, but we also want it to be outside the span of B. So now let's use that to form a linear combination. Let's say U is now V1 plus V2 plus V sub n plus some vector Q. And we know Q is non-zero because U was not in the span of the V's. So now let's solve for Q. Q is now equal to U minus V1 minus V2 up to V sub n. But we know that this Q that we've just created belongs to our vector space, doesn't it? Why? Because this vector space is closed under addition. Now what can we do? Well, now we have a vector that is linearly independent from the original V's, V1, V2 through V sub n. So now let's add Q to the list B. So now let's create a new list B that's V1, V2, Vn, and Q. If this new B now spans V, we now have a basis. It's a basis of V, and we are done. If B does not span V, then what do? Do it again. We repeat the process. So let's try to just look at an example of that, just so that everybody's on the same page. We're building a basis from a linearly independent set of vectors. Suppose that the original set of vectors B is given by 1, 0, 0 and 0, 1, 0. And suppose our vector space is R3. Now we could pick pretty much any U we want. Let's pick one that's a little bit more interesting than the generic one that you probably want to pick. Let's just say that somebody says, oh, I can pick a U that's not contained in the span of B. Let's say it's 5, 6, and 8. So now we can see that U does not belong in the span of our original two vectors in B. Following the idea in the proof, we know that U, which is 5, 6, and 8, is equal to V1 plus V2 plus Q. And now what's Q? That's not too hard to find. That's now 4, 5, and 8, isn't it? And that's in our three-dimensional space. And now we can create a new spanning list B. B now is 1, 0, 0, 0, 1, 0, and 4, 5, and 8. And now we can see that the span of B is actually all of R3, and we've now created a basis. So we'll pick up at that point, or I may do some more stuff in between next lecture. Maybe we'll get into chapter 3 next lecture, so I have to somehow complete. So stay tuned. Maybe I'll do something offline.